Okay, so the plan for today, I actually kind of just stole my my Monday presentation because I want to review what we talked about on Monday, but the plan for today, Wednesday, is to finish correlation regression. I think it makes a little more sense to, instead of trying to rush through correlation regression, chi-squared, and ANOVA in these last um, basically three class periods, last class, this class, and Monday. The supplement for chapter 11 on chi-squared is already posted. So we'll plan to take the rest of today to talk about correlation regression, and we'll punt the chi-squared information to the supplemental video that's already available on YouTube. And then on Monday, we'll cover ANOVA chapter 12. And as I mentioned before, that chapter 12 video is also posted already on YouTube. So if you'd rather kind of knock that out early, either knock out the homework before final exam week, or even if you wanted to take the final exam a bit early before Monday the 9th, you can review that ANOVA material from chapter 12. Those videos are all on YouTube and have been for a little while. So the plan is to finish correlation regression today, cover chapter 12 ANOVA on Monday, and we're going to punt the chapter 11 chi-squared tests for goodness of fit and independence to the supplemental video. So just take a look at that supplemental video sometime in the next few days or so, work through the homework. It's yeah, as I mentioned before, none of these last three topics, correlation regression, chi-squared, or ANOVA, are meant to be super in-depth or super challenging topics. They're really surveys of these ideas. Um, and then, as I mentioned before, the final exam is, well, kind of properly next week, but really starts this Friday the 6th through Friday the 13th. It's not comprehensive. It's only on chapters 7 through 12. It's taken on using Examity, similar to the midterm exam taken on my stat lab. The sample final is available now. I apparently said that on Monday, but it wasn't quite available yet. So I went in, changed that. It is available now. So you can note that you'll see it at the top of the assignments tab. I put all the exams at the top of that tab so that they're just easier to find when you click in. You don't have to wade through, homework sets or something like that. So you'll see the sample final exam available. You can use that to practice any of the material, to assess your understanding of the material. Of course, this will have uh, some stuff from correlation regression, chi-squared, or ANOVA on it. So, if you log into it today, there might be a couple of problems that are on topics you're not familiar with or you haven't seen covered, but most of it should have been covered by now. And also on Blackboard in supplemental material folder under the exam material subfolder, you should see one PDF with all of the formula sheets and distribution tables that you're free to use on the final exam. You can either print it off and have a physical copy there, it's something like 3 or 4 pages front and back, something like that. Or you can have it as a PDF on your computer, or you can have both if you want, however you want to have access to that. So that's everything from like normal chi-squared and t-tables to like formula sheets with some different formulas on them. I just dumped all of the formula sheets in there. So some of the formulas might not be relevant to chapter 7 through 12, but I put them all in there just so that if there is a formula that you want to have, you know that it's there. Um, and as I mentioned before, I would strongly recommend planning to complete the final exam no later than, say, something like Wednesday the 11th, something like that. Uh, that way, if anything does go wrong, you have kind of a full business day or two of buffer. Um, you definitely don't want to miss the final exam, and there are no due date extensions on exams. So make sure to get that taken and completed, relatively early in the time period. That also just gets it off of your plate. You can focus on other material at that point. All right, so any questions on any of the administrative stuff, on anything we talked about last time where we mainly focused on correlation? Any questions on anything? All right. So I want to quickly recap our discussion from last time. Oh, let me realign everything here. Um, there we go. So our goal with correlation or regression is to study linear relationships between two variables, x and y. So there's two things that are a little different than what we've kind of done in the past. Number one, we're studying two variables at a time, now x and y. So we're studying the interplay between two variables. And for most of the course, we've really just been looking at a single variable. Um, so we've been looking at, questions about, say, the mean for this single population or the standard deviation for this single population, something like that. Now we're looking at the interplay between two variables. And the second thing to realize is that we are looking to study a particular type of relationship. We're looking to tease out whether this type of relationship exists between these two variables. In particular, that is a linear relationship. And as we mentioned last time, our data consist of ordered pairs that have a natural ordering to them, a natural combination, right? So like the classic example is measuring height and weight for person one, person two's height and weight, person three's height and weight. Those are naturally associated because person one has this height and person one also has this weight. That height and weight kind of naturally go together. We're not studying two variables like where we just collect 100 people's heights, write those down over here, pick another 100 people, collect their weights, write those down over here, and just like mash them up. There's not a natural pairing there. So we're looking at kind of naturally ordered pairs, and we can make a graphical representation of these with a scatter plot, right? So we look at a scatter plot, it might look like this. And we talked last time about the correlation coefficient, denoted either rho for the population parameter or R for the sample statistic. And it's always a number between -1 and 1 inclusive. And it has two characteristics we're interested in. It has a magnitude, in other words, an absolute value. Is the number in magnitude close to 0 or close to 1? So a correlation coefficient near -1 has a magnitude near 1, or a correlation coefficient near +1 has a magnitude near 1. Correlation coefficient near 0, say -0.1, +0.1, something like that, has a magnitude near 0. That magnitude describes what we might call something like the degree of the relationship, particularly the degree of the linear relationship between the variables. In the context of correlation and regression, if I just say relationship, uh, I'm typically going to mean linear relationship. I might just forget to say linear relationship. So if I'm looking at the magnitude, that tells me something about the degree of the linear relationship. Is there a strong linear relationship between the two? In other words, does this scatter plot look fairly close to a straight line, these data points? Does it look like they would all fall pretty close to a certain straight line? If so, then there's a high degree of linear relationship, and my magnitude would be near +1. On the other hand, if the data points are just kind of scattered about, and it doesn't seem like any line that I draw through them is going to be, a better model or better fit to the data than really any other line, then the magnitude might be near 0. If I have a very low degree of linear relationship, if my magnitude is near 0, I don't much care about the nature of that relationship, right? If the relationship doesn't exist, it doesn't really have a nature. However, if I have a high degree of relationship, if my magnitude is near 1, I could get a magnitude near 1 with a large positive number, say a number like 0.8, 0.9, 0.95, or with a large negative number, that would also give a magnitude near +1. So like -0.8, -0.9, -0.95 would all have magnitudes near +1. So if I have a high degree of linear relationship, I'm also interested in the nature of that relationship. And that's where the sign comes in. Is it a positive or negative relationship? So as I mentioned, magnitude near 1, high degree of linear relationship. I want to investigate the nature of that relationship. Magnitude near 0, low degree of linear relationship. Not really sensible to describe a nature of a relationship that is non-existent. If the magnitude is near one, and this is very context dependent, in some senses, maybe 0.5 is close enough to one that we're interested. In other senses, we might demand a magnitude near 0.8 or 0.9 before we're happy to start describing and using that relationship. But if the magnitude is near enough to one that we say, okay, this is a relationship that we are interested in, if the correlation coefficient is near a positive one, if the sign is positive, then the nature is positive in the sense that larger values of one of the variables tend to be associated with larger values of the other variable, and vice versa. Smaller values of one tend to be associated with smaller values of the other. So things like height and weight, that would probably be a positive relationship, right? If somebody's taller, they tend to weigh more. If somebody's heavier, they tend to be taller. And again, this is a model. This is something that, kind of applies roughly generally, and not necessarily to every individual data point. On the other hand, if I have a correlation coefficient that's near -1, so its magnitude is still near +1, but the coefficient itself is near -1, then the nature is kind of negative. It's the two variables kind of oppose in some sense. That larger values of one variable tend to be associated with smaller values of the other variable, and vice versa. So one example of this is it was a bit bigger of a deal maybe 10, 15 years ago in the housing market crash. But folks who had more years of education, so folks who had some college or a college degree or kept going, the more years of college education they had, the lower their risk of unemployment. So it's kind of like if I look at somebody, during that crash, whenever employment was pretty tough, if I look at somebody and I see that they have, let's say 16 years of education, say maybe your normal 12 years plus a bachelor's degree, I might associate that with a certain unemployment level. Maybe there's a 4% chance that that person is unemployed. But if I saw that they had, 14 years of, or what did I say, 16, if I saw that they had 18 years of education, maybe I would associate that with a 2% rate of unemployment, right? That the larger their years of education, the smaller tend to be their chance of unemployment. Now, of course, there certainly were lots of people, with fewer years of education who weren't unemployed, and there were certainly people with a lot of years of education who were unemployed. It's important to remember that all important quote from George Box, all models are wrong, some models are useful. So this is, at the end of the day, a linear model. We're modeling the linear relationship. Okay, and we talked about correlation, so let me jump to full screen here. We talked about the correlation between, say, some different variables last time, and we looked at several of these plots. And the one we're going to work with today is this newer version. So we looked at kind of the old stock market data. This is newer data from the last 2 years. And we see, for instance, if we're looking at silver versus gold, Google, Tesla, Amazon, and PIMCO's high income, high yield bond fund, we actually see that their correlations, I've made this little correlation matrix over here using the COR-REL function, apply to the relevant data sets, right? Well, this one looks kind of funny because it's silver against silver, but let's do this one. So silver against gold, 2 different data sets. We see the correlation between, roughly speaking, the price of silver and the price of gold, or really the price of one of these shares from Spider Gold shares or from iShares Silver ETF is 0.94. So that's a number that is quite close to 1 in magnitude and has a positive sign. And that's what I'd expect, right? If I look at the market today and see the price of silver is high, higher than usual, let's say, I probably would expect the price of gold to be higher than usual as well, and vice versa. Something like silver versus Tesla, I mean, if I see that the price of silver today is high, that doesn't give me much information at all about Tesla, and vice versa, right? I think we can just naturally understand those two are less related. Okay, so what is regression then? So we discussed this idea of correlation. What about regression? So the goal of performing a regression analysis or finding a regression line is to construct a linear model to help model the relationship between X and Y. And so here's our idea is let's suppose that I have a scatter plot of some data for X and Y, and suppose that I look at the correlation and it does seem that there is a high degree of linear relationship between the two variables. When I say there's a high degree of linear relationship, what am I really saying? Well, what I'm saying is that I think that I can find a straight line. I can pick a straight line where if I draw that straight line superimposed over the scatter plot over the data, most of the data points are pretty close to that line. That's kind of what I mean by that, right? Now, note that that doesn't mean that whatever line I pick, most of the data points are close to it. That's certainly not true. But I'm saying I can find a line where most of the data points are close to it, right? And the question is, well, this line is like y equals mx plus b, or really in stats, we would typically say alpha plus beta x. So kind of slightly annoyingly in stats, the beta, the thing that kind of we in algebra think of as b, the intercept, is actually kind of the slope here. So here alpha is the intercept and beta is the slope. Again, we're just doing an exposition here, so there are nuances with, whether we are using population parameters, alpha and beta, or whether these should be considered sample statistics, say maybe we call them A and B. I'm not really worrying about that. So again, this is just an overview. This is just a survey. We're not digging deeply into any of this, so we're just trying to get these ideas somewhat straight. Little side note, this has nothing to do with significance or power. So I know we just finished up hypothesis testing where alpha was the significance level and beta was, so alpha was the type 1 error rate, the significance level. Beta was the type 2 error rate. It was 1 minus the power. That alpha and beta are not the same as this alpha and beta. These are completely different context, completely different alpha and beta. We just happen to be using the same Greek letters to represent something completely different in the regression world. So sorry about that, a little bit annoying, but at some point we start running out of letters to use and have to use the same letters for different things. Okay, so this is the goal of a regression line. I want to construct a linear model to model the relationship, hopefully the linear component of the relationship between X and Y. But here I'm being a little bit careful. We're using this as a model to model the overall relationship between X and Y. There are some X's and Y's where the relationship overall is well modeled by a straight line, like this scatter plot, for instance. These are also the X and Y data that probably have a high degree of linear relationship, that have a large correlation, large magnitude of correlation coefficient. Note that there are data sets that have a very clear relationship. say something like this, I mean, there's obviously a relationship between X and Y here. This might be something like, say, speed versus miles per gallon, gas efficiency in a car, right? If you're going super slow, I mean, it just takes a certain amount of gas to keep your car running, and you're not getting very far. If you're going really fast, you're battling against all of the, wind resistance, air resistance, rolling resistance of the tires and the bearings and all of that. The faster you go, the higher those forces are, and the more energy you're dissipating into the environment as heat and noise and so on. So you're losing efficiency at the top end of your speed as well. And also the engineers tune the engines and all of that to perform very well at certain speeds, and they're just inherently less efficient at speeds that deviate from that. There's definitely a relationship here, but is there any straight line that does a good job of modeling that relationship? Well, no, not really, right? I could also have a situation like this. Let me try to draw these dots a little bigger for you to see a little better. In a situation like this, it seems like there's no real relationship. Yeah, so no relationship. Over here, it seems like there is a relationship, just very nonlinear. What do I mean when I say that there's a relationship? What I mean is that if I tell you what X is, if I say X is like in this interval, does that constrain your guesses for Y, right? If I don't tell you where X is, your guess for Y is like, let me use blue for this. If I don't tell you anything about X, your guess for Y is somewhere in that interval. But if I constrain the X's, if I say okay, I looked at X, I observed X, and it's somewhere in this interval, my guesses for Y become significantly more constrained. When I know something about X, that tells me something, and in this case, quite a bit about Y. If I constrain the possibilities for X, that also constrains the possibilities for Y quite a bit. That's a relationship. Note that my nonlinear relationship down here is still a relationship, right? If I constrain my possibilities for X, my possibilities for Y go from like here to, I don't know, something like this. My possibilities for Y or I should be careful with saying the word possibilities. My expectations for the outcome of Y are significantly constrained, right? If I tell you you're driving between 30 and 50 miles an hour, what does your miles per gallon look like? It's not going to be like 2 miles per gallon, and it's not going to be like, 5 miles per gallon or something over here. It's going to be a reasonably high miles per gallon. There's still a relationship here, but over here, where there's no relationship, if I tell you nothing about X, this is your range of, say, reasonable possibilities for Y. If I constrain X and I tell you, okay, I looked at X, I observed X, it's in this interval. Well, if I look at the data points, the Y coordinates that are associated with X's around there, they still have like the same range, right? They still have, that didn't tell me anything about Y. So there are situations where I have no relationship. So no good linear model here. There are situations where I do have a relationship, but a line just is not the appropriate model. No good linear model here either. So the situations where regression is going to be a good model, where a linear model is going to be a good one, is where there both is a relationship and it's at least fairly linear. Now, so two kind of fun quotes. The first quote, I actually don't know the origin of this. I've tried to find it, but I heard it a long time ago, um, and I don't know where I heard it now or who said it, but um, it goes something like dividing the world into linear versus nonlinear phenomena or things we want to study is like dividing all objects in the world into bananas and not bananas. So in other words, if you take like every object in the world, I mean, sure, there are some bananas in the world, but like basically none of them are bananas. Right? If you take all the things we want to study, some of them are linear, but basically none of them are linear. Essentially, everything is nonlinear. But on the other hand, again, my favorite professor, Professor Layton from Pitt, one of his, I guess, catchphrases or slogans or whatever is the world is locally linear. Super important idea in, say, calculus. But there's two ways to kind of understand this. One is geometrically. Let's say that I look at a function. It looks like this. Okay, that's a nonlinear function. It's not a straight line. But what if I like zoom in on it? If I zoom in, if I look at the local properties around, say, a certain point, I mean, okay, maybe it's still a little bit nonlinear. It's not quite a straight line, but it's a heck of a lot closer to linear than if I'm very zoomed out, right? The same way that if I want to model, say, gravity on the Earth, not to get into a hot debate here, but I essentially model the Earth as flat, right? If I'm driving a car around or building a building or doing anything of reasonable scale, I pretend the Earth is flat and gravity just points straight down, and that's the end of the story because the Earth locally is basically flat, right? If I go left, right, forwards, or backwards, a couple feet or even a couple miles, it pretty much acts like it's flat. Flat relative to, say, not acting like a sphere. There might be a little hill or something like that that I have to go up, but basically flat. But if I zoom out to the, look at Earth from the space station or something, well, it's very clearly not flat at that scale. So if I zoom in far enough, these nonlinear phenomena tend to look linear. So in other words, if I came up here and said, well, maybe I'm engineering something to do with speed versus efficiency, and instead of looking at all ranges of speed for my model, maybe I'm running out of colors here, but maybe I'll focus on just the higher speeds. Well, if we focus on just the higher speeds, just this data that I've kind of boxed here, well, now we can see that a linear model is going to do a much better job of staying close to most of the data points, right? Not a great model for the overall data, but if I zoom in a little bit, maybe I have a region of linearity that I'm confident using a linear model there. In science and something like real or practical science or whatever, this is something that folks do. If somebody is working in a medical laboratory and they have to develop a test, they uh, they get a lot of samples, they run them through their machines and so on, and they quite often get nonlinear results out. But the question is, can they construct that test and that analytical technique and so on in a way that for the region of interest, right? I don't care about somebody whose sodium is like, 100, like they're probably dead. I care about somebody whose sodium is like 125 to 140 or something like that. If I narrow my search to that range, well, can I say, okay, I can approximate that with a linear model? Can I extrapolate from there or something like that? That's probably not a great example, but just to throw an idea out there. So narrowing your scope, kind of zooming in, so to speak, can often take a nonlinear problem and make it look linear, and then you might be able to do some of this regression analysis on that uh, on that smaller portion of the sample. Another way to look at this is a little more sophisticated way, but this is the kind of algebraic approach. So some of you may have taken calculus. If you didn't, that's not a problem. But we know that if we have some function f of x, say this nonlinear curve here is a graph of y equals f of x, I can approximate f of x by a linear function. So it's some alpha plus beta x approximately. Or here I'm going to choose to maybe just call this a naught plus a1x. I can get a better approximation if I add more terms. If instead of using a linear function, if I use a quadratic. If the thing I'm modeling is linear, I just make a2 0, so that my quadratic term goes away and I have a linear function, so I don't lose anything by adding this term. I can always just choose to make a2 0 if I wanted. But I could make a2 something else and have a quadratic term. Now my function, my approximate function can curve a little bit. I could add a cubic term. Now it can curve in some different ways, right? Quadratics only have one local max or min, but cubics can have two. And in fact, if I do this for an infinite amount of these polynomial terms, a quartic term, a quintic term, a sixth power term, and so on, for reasonable assumptions on my f, I can actually say that f is equal to some infinitely long polynomial. So this idea is called a Taylor series. Super interesting idea, super useful in applied science fields like physics and chemistry, economics, places like that. But again, I can kind of chop off these higher order terms and get an approximation. And it quite often turns out that these higher order terms, so long as I don't deviate too far from my point of interest, the point that I'm using to find all these A naught, A1, A2, and so on, so long as I don't go too far away from there, it turns out that these higher order terms have a relatively small impact on the overall value. It's really these first couple terms that dominate. They have a much bigger effect than this one, which has a much bigger effect than this one, and so on. We can see that by, if we look at, say, the deviation being fairly small, well, if I multiply A naught by no small number, then it's just A naught. It just is what it is. If I multiply A1 by a small number, that's a kind of small number. If I multiply A2 by the square of a small number squared, like 0.1 squared, 1/10 squared is like 1/100th. It's a really small number. So if this is small, this is of order 1, it's not small. This is small. This is really small. A small number cubed, like 1/10 cubed, is like 1 in 1,000. This is really, really small. So if I don't go too far away from my point of interest, this point where I'm kind of focusing on zooming into to make the nonlinear function kind of look linear, then I can get away with using just the linear bit. Now you might say, why would I do that? Why wouldn't I just work with the full nonlinear function? Well, because the nonlinear function is a heck of a lot more complicated and difficult to deal with. It's difficult to even plug a number in and get a number out. That's not a trivial thing. But making any kind of analysis or hypothesis test or statistical claim or confidence interval or anything like that based on the nonlinear function is going to be much, much, much more difficult, if it's feasible at all, than making similar statements about, say, the linear model, which is just a much simpler model to deal with. So the trade-off we're making here is we get with a linear model, the trade-off we're making is we get a much simpler model That's the plus. And that's a huge plus. So don't underestimate that. The minus is that it's not correct. It's just a model. It has caveats, right? How far away can we go before, right? If I take a big number, if I take like x equals 10, this is like 1, this is like 10, this is like 100, this is like 1,000. So now all of a sudden, if x is big, x squared is really big and x cubed is really, really big. And now chopping off all of these terms, I I just destroyed my model, right? So I have a narrower constraint. I have a narrower range of inputs where I can generate an output and be fairly confident in it. Um, so there are some caveats to it. I need to make sure that I'm in the correct situation where, making a simplification like this is fairly reasonable. Okay, so let's jump over to the Excel file and take a look at some of the material over here. So if you see along the bottom here, there are different tabs. This Corel chart, the correlation chart or the correlation matrix is here. If we go to the next tab over, zoom in a little bit. If we go to the next tab over, we see here I'm focusing on silver versus Tesla. Now remember, so we have 2 years of data here, 2 years of weekly data. So roughly 100 data points. If I look at my scatter plot, well, it looks just kind of like a big blob, right? If I imagine where the center of the data is, maybe somewhere around like 24, 225, something like that, right around here. If I were to draw 2 coordinate axes, it looks like there's about as much data in each quadrant as any other quadrant. I'm not really seeing strong evidence of a linear relationship here. And indeed, if I look at my correlation coefficient, 0.2, that's pretty weak evidence of a linear relationship. If I ask Excel to draw this regression line, if I ask Excel to find the values of alpha and beta, roughly speaking, that give the best model, it'll return something like this. And we'll look at how to actually generate this in a minute here. We'll also look at how it makes the decision of what slope and intercept to use and so on. So we're going to build off of this, but just looking at the results at this point, we see this multiple R. Well, this is really the correlation. It's called something a little funny here because there are other types of regression you can do where you maybe have more explanatory variables. So it's kind of like a correlation that takes into account how many variables you're using. But since we're only using one variable here, this multiple R is just the same as our correlation coefficient. So that's one thing that we see. We see our correlation of 0.2 or so, which is exactly what we expect from where we computed it ourselves. We also see that our coefficients here, this intercept being 139.7, and the slope, the coefficient of the silver price, being 3.13 or so. So what I'm saying is that my regression model here, I guess I have to come down here a little bit. My regression model for, what was this, silver versus Tesla, is that my guess for Tesla's price, given a silver share price, is 139.7 plus the slope of 3.13 or so times the iShares silver price. So for example, if the iShares silver price, what were their numbers? I think it was like 100 in the hundreds, right? Or no, okay. Oh, it looks like it just goes by roughly silver spot price per ounce. So let's say if we use somewhat reasonable numbers here, if silver was 30, then my estimate for Tesla, 139.7, just cannot write well these days. Okay, there we go. 139.7 plus 3.13 times 30. Now, very importantly, this is an estimate, so I'm going to put a hat on top of it. Just like p hat, if we remember p versus p hat, this is an estimate. This is what my model suggests. My model suggests that if I look at the silver, iShares silver price, and it's $30 per share, then I would expect my best guess at the Tesla price would be, let's bring up the calculator here, figure out what this is, 139.7 plus 3.13 times 30, or 233.6. So that's what my model says. If I looked at the iShares silver price today and saw that it was 30, my best guess at what the Tesla share price would be is 233.6 based on this model. Very importantly, I'm not saying that like if the silver price is 30, Tesla's share price has to be 233.6. This is just a model. This is just me making a guess. Just like any guess, just like any model, this might be a really good guess. It might be a very reliable guess. It might be a terrible guess. So we want to use a little more of the information in here to tell, do I think this is a good guess, a terrible guess, somewhere in the middle? And there are a few things that I'm going to look at here. In particular, this R squared number and this p-value number down here. Okay, so rho, or R, is the correlation coefficient. It's that thing that describes the nature and degree of linear relationship between two variables. If I look at R squared, which is literally R squared, literally just calculated as the correlation coefficient squared, multiply it by itself. If I multiply a number between -1 and 1 by itself, it's going to be between 0 and 1. So R squared, this is what we call the coefficient of determination. DET, determination. So it's kind of interesting. All we have to do is take the correlation coefficient, multiply it by itself. So if the correlation coefficient was -0.5, -1/2, we multiply it by itself. -1/2 times -1/2 is +1/4, 0.25. That would be R squared. Take the correlation coefficient, multiply it by itself, or square it. That gives me the coefficient of determination. What does that tell me? That tells me the proportion of the variability in Y that's explained by the variability in X. Or really, what do we mean by this? It's really the explanatory power of the model. So if R squared is near 1, this model is very, very useful, right? If I know the value for X, I can very accurately predict the value of Y. If R squared, so R squared near 1, very powerful model. It's allowing me to predict Y very well on the basis of knowledge about X. R squared near 0, not at all powerful. It's a bad model. If I know something about X, that essentially tells me nothing about Y. This is perfectly in line with our understanding of correlation coefficient itself, right? I mean, the magnitude is between 0 and 1. If I take a number close to 0 and square it, it's a number close to 0. If I take a number close to 1, like say 0.99 and square it, it's going to be about 0.98, still close to 1. If I take a moderate number, let's say a correlation that looks like 0.6 or 0.7 in magnitude, and I square it, well, 0.6 squared is 0.36, 0.7 squared is 0.49. So, those correlations of say 0.6 or 0.7 lead to a model with explanatory power of like 1/3 or 1/2, where one variable is explaining a third to a half of what's going on in the other variable, and a half to 2/3 is left unexplained. Now, again, in some fields, where we have tons of inputs and they come together in a very complicated way, maybe we're happy to get 30% explanatory value from a model. That might be a win. In other fields where we have fewer inputs and it's more well defined how they interact, maybe we're very unhappy with a model that has 30% explanatory power, right? It's all relative to the other options. If I have a model that, does a great job of explaining things, and then I get a coefficient of determination for my new model that does worse, well, my new model probably isn't all that great because I have other better options out there. If I don't have anything that does any decent job at all of explaining the phenomenon, and I can get, 30 or 40 or 50% explanatory power, maybe that's a win. So, you know, uh, correlation magnitude near 0 or 1 essentially corresponds to an R squared near 0 or 1. So this is my coefficient of determination. You see my coefficient of determination is 0.04. That's pretty darn close to 0. I don't think there's much explanatory power to this model. I'm only explaining 4% of Tesla's stock price using the iShares silver price. That's probably not a very big win, right? I could probably just look at the overall market and do better than that. Just look at how the S&P or the Dow Jones is doing today. That's probably going to tell me more about Tesla stock price than the iShares silver price. The other thing I want to look for that's somewhat formal is this p-value for slope. So my population regression model would be y equals alpha plus beta x. And the regression model that I calculate off of data from sample data, y equals, let's say, a plus bx. Now, if beta equals 0, if in reality y has no linear dependence on x, there's no linear relationship between x and y, then beta would be 0. No linear relationship between x and y. So I set up a hypothesis test. My null hypothesis is that beta 0, that there's no linear relationship between x and y. If I just pick two variables at random, they're probably not going to have a linear relationship between them. And my alternative hypothesis is that beta is not 0, that there exists a linear relationship between x and y. And I might say something like, I run my hypothesis, and if the p-value less than 0.05 or 0.01 or something, then reject H naught in favor of H1. So a strong argument in favor of, or at least a component of a strong argument in favor of this being a good linear model is having a low p-value, particularly for the slope. So I'm looking for a high r squared, and I'm looking for a low p-value for the slope. These are kind of the formal things that I'm looking for. I'm looking for high explanatory power, and I'm looking to be able to reject the null that there's no linear relationship in favor of the alternative that there is a linear relationship. I actually do see a p-value of 0.03 here. I mean, that's less than 5%, so it's statistically significant, but not less than 1%, so it's not really highly statistically significant. So this is okay, but not amazing. It's not a p-value of like, 10 to the minus 10, uh, but it's, we can reject the null in favor of the alternative. So I get an okay, not amazing, but okay p-value. But I have a very low coefficient of determination. There's very low explanatory power in my model. It's not doing a whole lot. The third thing that I probably want to do is a more subjective thing. Oops, wrong button. There we go. So here's my Silver and Tesla actual data. But now I have a regression model. I have an intercept of 139.7 and a slope of 3.12. That was what I demonstrated up here. And I can say for a given silver number, what is my estimate for Tesla? So I have an actual data point. I know that at one point silver was 27.92 and Tesla was actually 345.16. Now my question is, under my model, what would my model estimate Tesla's price to be when silver was 27.92? My model estimates Tesla to be 227. So I can come down here and for each of these data points where I have actual Tesla data, I can compute an estimate under my model for Tesla's price. I can overlay my estimate numbers on the actual graph of the actual data. So these blue dots here, the actual data, this is actual observed data from the real world. These were actual silver prices versus Tesla prices. And the red line here is my estimate. I mean, of course, silver versus Tesla estimate, this is a linear model. Those points are all going to lie in a straight line. So I just worked with Excel a little bit here and made that look like a straight line. And I look at this and I basically ask myself, does it look like my straight line, my red model, is like roughly reasonably close to my data? Not really. My data doesn't really look like it's well modeled by this line at all. So all in all, I don't think I would want to use this model. It doesn't look very good, right? It doesn't look like this red line is doing a good job of modeling these blue data points. Okay, my p-value is less than 0.05. It's statistically significant, the model. There's probably some amount of linear relationship between the two, but it's not likely to be really practically useful at all, right? The statistical significance versus practical relevance discussion comes into play here. So overall, silver versus Tesla, I probably would not want to use this regression model. I would look for, if I wanted to explain Tesla's stock price, I would look for a different variable. Okay, let's go to Google and Tesla. And I should have zoomed these all in first, but over here to Google and Tesla. We're going to go more quickly through this one because we've already done one. I don't know why that chopped off the top half of the chart there, but whatever. I swear, ever since Microsoft switched this 365, it's just so glitchy and also tends to take forever to open things up. But so here's my Google and Tesla data. So Google stock price versus Tesla stock price. Again, weekly data over 2 years. My correlation here is 0.35, so a little higher than the 0.2 for silver and Tesla. When I run the regression, again, I see my two important numbers up here. My R, my correlation, but importantly, my coefficient of determination, the explanatory power of the model, is only about 12%. So if I look at Google's stock price, that is only explaining about 12% of what's happening with Tesla's stock price. I do notice my p-value for the slope is highly significant, 0.0003 or so. Well, 0.01 would be 1%. So 0.001 would be like 0.1%, or this is really like 0.03%, right? This is highly significant. It's much less than 1%. So I'm quite certain that there is some linear component to this relationship, right? In the functional case up here, I'm quite certain that A1 is not going to be like 0, but is it significant enough that this model is worth using? I shouldn't say significant. Is it substantial enough that this model is worth using? So I have a pretty low coefficient of determination. I have a pretty low explanatory power to the model. I'm only explaining about 12% or about 1/8 of what's happening. And again, if I come over here and plot my regression line on top of the scatter plot, I mean, this looks a little better than the last one, but still there's a lot of data that's not anywhere close to that line. So I still look at this and I'd be pretty skeptical about using this result. Between the low coefficient of determination and the plot just not looking like a good model, I probably wouldn't go with this. All right. So let's look at two different securities. So here we have Google versus PIMCO. So this is Google's share price versus the price of a share of the mutual fund, PIMCO's high yield bond fund, the junk bonds, as they're sometimes called. And if I just look at this picture, this scatter plot, this data just looks like it falls more nicely along a straight line. I see that borne out in my correlation coefficient too, around 0.8 instead of around 0.2 or 0.3 or so, like the last couple of examples. I would expect my linear model to be better here because it seems like there is a higher degree of linear relationship between these two variables. If I look at my regression output, let me resize these. There we go. If I look at my regression output, I see my R squared is about 60%. My coefficient of determination is about 60% explanatory power. In other words, knowing something about Google's share price explains, say, about 60% of what's going on with PIMCO's share price, and about 40% is left unexplained. This is a heck of a lot better than the like 5 or 10-ish% that we were getting for the explanatory power of those last two models. I see my p-value for the slope, the p-value corresponding to Google, the other variable, is highly significant. Right, 10 to the minus, this e minus 22 means times 10 to the power minus 22. 10 to the minus 22, if we see a 10 to the minus 2, that's 1%. that would be highly significant. 10 to the minus 22 is extremely highly significant. Now remember, high significance doesn't necessarily mean high practical relevance. This might be a highly significant result, but I might, still not want to use this model. However, the 60% explanatory power is a pretty convincing piece of evidence that this is going to be a good model. I also look at the picture, and I do see that this regression line, this red line, does really seem to visually do a much better job of staying close to most of the data points. I mean, there's a few of them, maybe like kind of on the bottom in the middle, where they're kind of far away, but overall, this red line is fairly close to most of the data points. This is probably a model that I would use, right? It's not the best model that I've ever seen in the world, but it's certainly not a bad one. It's not like those previous two that have very low explanatory power, and the picture just, it didn't look like it was modeling that data at all. Okay. Any questions so far? Okay, so let's take a little jump back over here and discuss, to some extent, what Excel is doing in the background to create this slope and intercept numbers. So what is Excel doing? Well, we have actual data, X and Y. So I have, say, X1, Y1, X2, Y2, down to, say, Xn, Yn. I have this actual paired data, right? This is data coming from the real world. Now I have a model that says Y equals alpha plus beta X. Again, I'm not being careful with alpha and beta versus A and B here. We'll just call it alpha plus beta X. For a given X, for a given X1, my model would say that Y1 hat, the model estimate for Y1 would be alpha plus beta X1. So alongside this data, I could think of there being another column given a choice for alpha and beta. I have my Y hats, my estimates for Y under the model, say Y1 hat, Y2 hat, and so on down to Yn hat. What does this look like on the picture? On the picture, I have, say, an actual data point 1 at X1, Y1, and then there's kind of another point here at X1, Y1 hat. It's probably going to be a different value for Y. Or I have another point, say point number 2, and I have an estimate point. So I have X2, Y2, that's the black point, and I have X2, Y2 hat, that's my estimate for that height under the model for that given X, X2. And then maybe I have, point 3, and so I have actual data point 3, the black point, X3 comma Y3, that's data from the real world. I also have a point that represents my estimate from the model, that's X3, Y3 hat, the estimate for Y when X is X3. Now these blue points are all collinear because this is a linear model. These are all going to be on the same line because that's a linear model. And I see that my linear model is going to not match up with some of my data points, right? I think this blue model, say for these 3 data points, is, for instance, a better model than this red model. I mean, this red model is still a straight line, but I can see that the vertical deviation of the red model is typically much greater. The error is much greater. It's much further away from the actual data than that vertical deviation for the blue model, right? than these numbers here. These deviations are much smaller. So I want to prefer models, I want to prefer choices of alpha and beta, of intercept and slope. I want to prefer lines where that deviation between the actual data points and the line is fairly small. So what can I do? Well, I can look at squared deviations. I can look at deviations, yi minus yi hat, the observed value minus the expected value under the model, for instance. Now, again, these, just like we've seen before a few times, these deviations can be positive or negative. I eventually want to add them up so that I'm taking into account all of the deviations, but I don't want to add up some positives or some negatives because they'll cancel out. So I square them. I take the deviations, I square them. I have now some squared deviations. I sum over them. I add up all of the squared deviations over my n data points. And this is what we might call the SSD, the sum of the squared deviations. Or sometimes the sum of the squared errors. I think that's the more common term for it. I could write this more explicitly as sum I equals 1 to n. Yi is just, that's just what it is. That's the data from the real world, the y data. But what's yi hat? It's alpha plus beta xi. When I tend to have lots of big deviations, this number tends to be very large. When my line tends to be close to most of my data points, this number tends to be small. So what I want to do is I want to choose alpha and beta in such a way to minimize SSD, right? SSD is a function of the yi's and the xi's. Those are our data. Those are actual data points. We just plug those in, and those are what they are. They're a bunch of numbers that we got from the real world. And then I can choose for my model what alpha and beta are going to be. And I want to choose them in such a way that it minimizes this sum of the squared deviations or sum of the squared errors. I want to choose alpha and beta to minimize that. And it turns out you can, this isn't too bad of a problem to solve. With a little bit of calculus, you can solve this and you can get alpha equals some formula and beta equals some formula. These formulas are pretty nasty looking in terms of summations. Actually, kind of interestingly, beta is, if you write it, if anybody has taken any linear algebra, you might recognize this, or any matrix operations course. So this is basically what it turns out to be. Is x transpose x inverse, x transpose y. So we can see, actually, if we think about this problem in the right way, the solution, this solution for beta, actually turns out to be able to be written pretty simply. I mean, now what all of this means is a little bit more complicated. Again, if you kind of remember, if you've done some matrix operations in a previous algebra class, maybe you've seen something like this. Or if you've had some linear algebra, you might have seen something like this. Most folks, taking this course haven't, so that's not a big deal at all. But the point is that kind of if you write these in the way your book has them written, they look like terrible formulas, but actually they're not bad formulas at all. It's just writing them out in summation is kind of annoying. And it's also not bad for your computer to compute these operations. So there is a closed form solution for alpha and beta, and you basically just plug in the data points, the x's and the y's, into here. These x's are just lists of all the x's, and this y is just a list of all of the y's. and that's the solution. So that is the choice for beta, and then you can pretty easily find alpha from there. But that's the choice for alpha and beta that you need to minimize the sum of the squared errors. So that's what Excel is doing in the background for you when it comes up with these numbers, or when it comes up with, say, these numbers, right? That's what Excel is doing in the background to generate these numbers. It's doing more complicated things to generate, say, these numbers, um, but uh, but to generate these, this is the process it's going through. Okay, so there's our Google PIMCO model, a pretty good model. So let's take a look at Google versus Amazon, right? These are in the same sector. These, both tech companies. There's the famous like FANG, FAANG. What is it? Facebook, Amazon, Apple, Netflix, and Google. Like, if you want to make a whole bunch of money as a software engineer or something, go to one of those five companies, and you'll be very happy with your job and your salary. But of course, they're very difficult to get a job there. I think there's another acronym these days. There are a few of those have fallen by the wayside a little bit, and a few others have come up. Uh, but yeah, Amazon and Google, both tech companies. I mean, Amazon, I guess, is you know, they're kind of like a store, but they're more of a tech company than a store almost, right? They're um, anyway. We can look at Amazon versus Google. Looking at the scatter plot, it looks like it's very close to a straight line. We see a correlation of 0.95. I mean, you can't get much closer to 1 than 0.95. If we run the regression, I see my correlation 0.95 or so. My R squared, my coefficient of determination, is about 91%. Remember, that's the explanatory power of the model. In other words, if I look at Google's stock price, what it's doing, that in a sense, my knowledge about what Google's doing explains about 90% of what Amazon's doing, and there's about 10% left unexplained. I'm quite happy with this explanatory power. This is a really strong model as long as everything else looks good. Of course, the p-value is extremely significant, 10 to the minus 56. Remember, this e minus here means times 10 to the minus. So my p-value, 10 to the minus 56, very happy with that. That's highly significant. Pretty much, if you're happy with the explanatory power, the coefficient of determination, for all practical purposes, your model is going to be significant. I mean, for your model to not be significant, you'd have to have such a garbage R squared, 3% explanatory power or something that you're like, it's not even worth my hassle. But we do see, that it's highly significant. And again, we jump over here and we look at the actual model on the actual data, and it looks like a very good model, right? If I saw a model where, let's say I had data like this, say something like that, my model might go through this data nicely enough, and the numbers might look good, but I might see a systematic error here, right? I might see that there's like a fundamental bit of nonlinearity that my model is not picking up. And I might be a little more skeptical of using this model, especially making, say, inferences outside of the bounds of where my data actually lie. So that's why I always just want to take an actual look at the model overlaid on the data and see, like, does it just look like a good model, or does it look like I'm missing something here? Something that these couple of numbers aren't really picking up. As an aside, let me bring this down. As an aside, there are these ideas of interpolation and extrapolation. So if I consider the range of x's where I actually have data, so this is the range of x's between x min and x max. If I'm making estimates or if I'm using my model within this range where I actually have x value data, that's interpolation. It's kind of inside of the data that I have. As a general rule, interpolation is much more reliable and much more trustworthy than extrapolation, where I'm going outside my data, where I'm trying to guess what's going to happen for an x that's bigger than my x max or that's smaller than my x min. So extrapolation is less reliable than interpolation. And I think that makes sense because I'm going to somewhere where I don't have any data from an area where I do have data. Now note that we might apply interpolation if, say, I have some data here and I have some data there, but I'm not sure about what happens here. Maybe I can develop a linear model and make a guess as to what happens there. But because it's kind of in between two places where I do have data, that's generally going to be more reliable than if I'm trying to like go out past where my data are. I really have no information out that far away. And obviously, the further away that I get, the worse it's going to get. And in fact, sometimes you'll see regression lines drawn. You might have, some data. I'm not drawing these super thick, but you might have some data. You might have your regression line. And then you might see these kind of two lines or two curves going along. And I'm going to try to draw them pretty nicely here. And they might look something like this. So these would be like the red is the best guess and the green is something like a confidence interval. So in other words, for this value of x, if I go up here, my best guess for y is that number. And my confidence interval would be this interval from this green number to that green number. So sometimes you'll see the regression line, the best guess line, plotted along with these two kind of confidence interval bounds. And it always looks like this, right? The further away from the middle that you get, the more you're extrapolating, the wider your confidence interval has to get because there's just much more uncertainty further out there. Okay, so now let's jump over to Excel and let's actually look at computing one of these. So let's look at, actually, we'll skip over gold PIMCO. We'll jump right to silver gold because this is going to be a pretty good one. So silver versus gold. I'd like to compute the correlation coefficient first. And I do that by doing equals COREL equals correlation of, I need to put in two data sets. So I'll start with my silver and I'll click, then scroll, and I'll do shift, hold shift and click. That selects all of my silver data, comma, and I'll do the same thing for gold. I'll click at the top, scroll down, hold shift and click, and that selects all of my gold data. Alternatively, I could name these two data sets. Oops. So you could do it that way. You could also just select all of the silver data Oops, didn't mean to do that. So I can select all this over data doing the same thing, clicking, shifting, and clicking, and then call it, SLV or something like that. And then do the same thing with gold, click at one end, hold shift and click at the other end and call this like GLD. So I could rename my data sets if I wanted to. And that makes it a little less cumbersome to do all of that while I'm kind of inside of my function and might click something a little wonky and mess up my function. Either way you want to do it. You can either do equals correl, open parentheses, and then select the data, or name the data and then type their names in. But I do see a correlation here of 93, 94%. I'm probably going to be pretty happy with this model. Having this high of a degree of linear relationship, I'm probably going to get a pretty good model out. How do I have Excel make my model now? How do I have Excel do this, all of this work for me? Well, I go up here to the very top. See, there's different tabs: home, insert, page layout, data. Under my data under my data tab, I should have this data analysis button over here. So you should have this from before in the course when we did a couple of things with histograms and one variable stats, but just in case you don't, if you go to File and Options, in the Excel options here, there is add-ins. We go down here to the bottom, Manage Excel Add-ins, hit Go, and you can just make sure your analysis toolpack is added in. If it's not, check the box, hit OK. It'll take a couple seconds and then it'll pop up here in this data tab. So we go to data analysis. And sometimes on 365, it takes it several seconds for it to load for me. I think because I've used it recently, it loads a little quicker, but yours might take a few seconds to load. But then I'm going to scroll down and I see that there's an option for regression. I'll select that, hit OK. Now, once the X and Y range, I'm going to choose my Y range, my outputs to be gold. I'm going to include the labels, so I'll check that. But my Y range is going to be gold, starting with D1, starting with the gold label, and scrolling all the way down to the end. I'll, again, shift click. Super helpful so that you don't have to like click and try to scroll at the same time, especially with a trackpad. That's kind of tough to do. So that is my Y range. I'll input my X range, my explanatory variable, the independent variable, as silver. So I'll click silver. I'll use its label as well, SLV. I want to use the label so that when it gives me the result, I kind of know what's what. I know which variable is which variable. Again, I'll shift click to the end. This always needs to be paired data. So it's always just a good idea to just take a look at my cells. Okay, D1 to D105 and C1 to C105. That looks like I got everything, right? If I did D1 to D105 and C1 to C104, I probably like missed a cell at the end. I'll output in new worksheet ply. I won't worry about any of this other stuff. And I'll hit OK. And this cranks out, whoops, this cranks out sheet 1 down here, silver and gold. I can jump over to sheet 1. I'm going to rename it silver, gold, just by double clicking where it says sheet 1. Rename it silver, gold, regression, REG. I'm going to select all of my columns by double clicking on column A, scrolling over to column I. And then if I just double click to the right of the column I marker, that resizes all my columns. Not strictly necessary, but just makes it easier to read. I'll zoom in just a tad. And I see my numbers up here, my correlation coefficient of 0.94 or so. My explanatory power, my coefficient of determination, is about 88%. Explanatory power. So I'm pretty happy with that. I'm explaining about 90% of what's going on with the gold price by looking at silver prices. I see my p-value for the slope 10 to the negative 48. Can't get a whole lot better than that. I'm probably pretty happy with this model. I might also want to go and actually graph the model. That's a little bit more cumbersome to do. And I don't think we can really do that in the next few minutes. So we're going to leave that off of this example, but just looking at the picture here, I think the graph of the model would be quite nice, right? I mean, we can imagine that if I take a screenshot and I come over here to OneNote, I can imagine my model is probably going to look something like this. And it's going to be pretty close to most of the data points, or basically all of the data points. Right. So I see that my intercept is at about 18. So 18, maybe a little less than half of the way up to 50. And my slope is about 7.5. So as I go over, say 10 units, I'll go up 75 units. Well, so I go over 10 units here. I'd go up 75 units from maybe 175 to 250, right? That looks like I'm right about on there where I drew my line originally. That looks like very close to what I actually got for these slope and intercept. Okay. So I'm quite happy with this model. So if I know something about silver, I can probably make a pretty strong inference about gold, at least when silver is kind of roughly in this ballpark range of 17-ish dollars to 31-ish dollars. If silver goes up to 50 or goes down to 10, like, then I'd be much more skeptical about making any predictions about gold on the basis of silver, because that's extrapolating well beyond where our data is, right? That kind of the world is locally linear, that zoomed in idea. If I go too far away, that doesn't really hold so well anymore. And then last but not least, because I feel like if we don't have any negative regressions, we are leaving something out. We'll look at the VIX versus Amazon. So the VIX is the volatility index. It's published by the CBOE, the Chicago Board of Options Exchange. And it's basically the volatility of the market. And it tends to be the case that when the market is crashy, people are selling a lot, things are much more volatile. And when the market's doing well, when it's a bull market, things just kind of plod along pretty steadily and are not all that volatile. So we see the correlation between, say, Amazon stock price and the volatility index is about negative 0.5 or so, negative 0.48. That's my correlation. So I see a negative relationship, but not a super strong degree of relationship. Let me go back up to my data analysis tab and run the regression. Regression's already selected, so I'll hit OK. And I actually see that it's already kind of input the same cells that I used in the previous sheet for my X and Y range. And that looks good. Because I made all of these sheets pretty similar to one another, I'm pretty happy with that. I'll keep my labels here, going from D1 and C1, so I did include my labels. Still outputting to a new worksheet ply. I'll rename my sheet 2 to, say, VIX, Amazon, regression. I'll resize my columns just to make it a little easier to see. Zoom in. And I see this isn't such a great model, right? My coefficient of determination is about 23%. That's my explanatory power. My uh, Amazon stock price uh, is only something like a quarter explained by looking at the behavior of the volatility index. I note that I do see actually a highly significant value though. 10 to the minus 7. This is certainly less than 10 to the minus 2, 0.01. It's like pointing a whole bunch of zeros and a 1. This is highly significant from a frequentist, from a hypothesis testing perspective. Maybe 23% explanatory power is good if I don't have a better model. If my choices are explaining nothing or explaining 23% of the behavior, that's better than nothing. But I feel like with all of the different securities and stocks and everything out there, I probably can do better than this. I also just look at this. Oh, and important to note here, this is a negative linear relationship. So we see that the slope coefficient for VIX is negative, -5. So the higher VIX is, the lower we're predicting Amazon's stock price to be. The more volatility there is in the market, the lower we're predicting this stock price to be. And we can even just imagine, again, in 1 minute, I don't have time to do this in Excel, but we can just imagine what the regression line might look like, maybe something like this. That just doesn't look like a great model. There's a bunch of data that's pretty far away from any line that we might want to draw through there. So again, if we want to do this properly, we could, I was planning to do that, but just ran out of time. We could come over here to Excel, do the same kind of thing that we did over here with these estimates and actually get a proper graph of the actual regression line, but we're just kind of ballparking it here. But we see that this is not going to be nearly as nice of a model as, say, something like this. These points are not nearly as tight into that linear model as these ones are. Okay, so that wraps up our discussion of correlation regression. Again, there's so much we could talk about here. This is really just a survey, an introduction to the topic. So focus on the material we covered in class. Also, take a look at that Chapter 11 chi-squared supplement that I put on up on YouTube. So both the chi-squared goodness of fit and tests for independence. And then on Monday, we'll hit ANOVA and just keep in mind this information about the final exam. Otherwise, I will see you all on Monday. Have a good weekend.
Have a